Our topic for today is from week 7, greedy algorithms. Okay, so the topics covered are, so we have to define the greedy algorithms, graphs, identify the taxonomy of searching algorithms and analysis of algorithms, identify the list of computing times of algorithms, identify the different types of greedy algorithms, know the advantage and disadvantages of greedy algorithms. So what is a greedy algorithm? So a greedy algorithm is a simple, intuitive algorithm that is used in optimization problems. The algorithm makes the optimal choice at each step as it attempts to find the overall optimal way to solve the entire problem. Greedy algorithms are quite successful in some problems, such as Huffman encoding, which is used to compress data, or Dijkstra's algorithm, which is used to find the shortest path through a graph. So it is an algorithmic paradigm that builds up a solution piece by piece, always choosing the next piece that offers the most obvious and immediate benefit. So the problems we're choosing locally optimal also leads to global solution are best fit for greedy. So there are some advantages and disadvantages for the greedy algorithm. Number one, it is quite easy to come up with a greedy algorithm for a problem. Number two, analyzing the runtime for greedy algorithms will generally be much easier than for other techniques. Three, the difficult part is that for greedy algorithms, you have to work much harder to understand correctness issues. So optimization problems, ingredients, so instances, the possible inputs to the problem, solution for the instance. Each instance has an exponentially large set of valid solution. Cost of solution, each solution has an easy to compute cost or value. Specification, we have the precondition and postcondition. For the precondition, the input is one instance. Postcondition, a valid solution with optimal cost. So every 2-year-old knows the greedy algorithm because in order to get what you want, just start grabbing what looks best. Surprisingly, many important and practical optimization problems can be solved this way. A greedy algorithm always makes the choice that looks best at the moment. So before we proceed with the greedy algorithm, I want to give a recap about the graph because graph is of course connected with the greedy algorithm. Okay, so to recall about the graphs, so G is an ordered triple. G is equals to V, E, F. So G stands for graph. V is either the nodes, points, or vertices. Okay, and then E is a set or elements of which are known as edges. So sometimes E stands for edges, or it can also be for what? It means arcs also. Okay, and then F is about function. So maps each element of E to an unordered pair of vertices in V. Okay, so vertex is the basic element. It can be drawn as a node or as a dot. So when you say node, it's a circle. Okay. So vertex set of G is usually denoted by VG or Z. So a set edge is a set of two elements, so drawn as a line connecting two vertices. So again, when you see a line, it can be edge or what? It can be an arc. So the edge set of G is usually denoted by EG or E. So this is an example of a graph. Okay. Okay, so we have six vertices. So we have vertex 1, we have vertex 2, we have vertex 3, we have vertex 4, we have vertex 5, we have vertex 6. Okay, so you can write it as a set. So V is equals to, so vertex 1, 2, 3, 4, 5, and 6. So what about the edges? How are you going to write the edges? So again, edges are the lines connecting the vertex or the vertices. So let's start with the number 1. So we have the first edge here. Okay, so we have 1 and 2. Next, we also have an edge connecting from 1 to 5. So that's how we arrive at 1, 5. So we have an edge 1, 5. Next, what about 2? We have an edge connecting from 2 into 3. So that's how we arrive at vertex or edge 2, 3. Next, we also have an edge or an arc connecting from vertex 2 to vertex 5. Okay? So we have 2, 5. Next, so we have from vertex 3, we have an edge connecting into 4. That's how we arrive at 3, 4. Next, we have an edge, okay, connecting vertices 4 and 5. So that's how we arrive 4 at 5. Next, we also have an edge from vertex 4 into vertex 6. So we have 4 and 6. So that's how we arrive at these edges. Okay? So let's try to discuss the different types of graph. Okay, so we have the simple graph. So when you say simple graph, simple graphs are graphs without multiple edges or sub-loops. Okay? Next, we also have the directed graph. Okay? When you say directed graph, an edge might have a what? An edge might have a direction. Okay? So you have an arrow here. This is the arrows. Okay? So meaning to say it has direction. Okay? So again, when you say directed graph or digraph, edge have direction. So an edge is an ordered pair of nodes. So again, as you can see here, we have the multiple arcs, we have a single arc, or we have multiple edges, or we have single edge. As I mentioned before, the line that connects the two different vertices are called edge or arc. So if you can, as you can see here and from the screen, from the vertex 1 and vertex 2, we have two arcs. Okay, so that's why it is called as multiple arc. Okay, while in vertex 2 and vertex 5, we have a one arc or one edge. Okay, so either you call it as an edge, either you call it as an arc, it's acceptable. Okay, so next is the loop. I hope you are all familiar with the loop. When you say loop, okay, this one is a loop going the input or the input is what? The input will loop into itself. Okay, that's the loop. So aside from that, as I mentioned before also, you can call the vertex as the node. So it's the synonym of vertex, this number 4 here. Okay? So next is weighted graph. So we have the simple graph, we have the directed graph. The next is the weighted graph. What is a weighted graph? It is a graph for which each edge has an associated weight. So meaning to say, for example, this one. Okay, I have vertex 1, I have vertex 2. I have a directed arc, from vertex 1 into vertex 2. And I have a weight here from vertex 1 to vertex 2 with a value of 1.2. Okay? So this is the weight. So the weight is in the arc or in the edge. Okay, so meaning to say, for example, here from vertex 2, okay, from vertex 2 going to vertex 4, I have a weight of 0.2. From vertex 4, okay, from vertex 4 into vertex 1, I have a weight of 0.5. And then from vertex 4 into vertex 5, I have a weight of 0.3. And then from vertex 5 into vertex 4, I have a weight of 0.5. And then from vertex 6 to vertex 3, I have a weight of 1.5. Just follow the direction of the arc if you're going to read the vertex. Okay? So same here. Weighted graphs, it's possible with the directed graph and the undirected graph. So from the right side of your screen, this is undirected because there's no direction indicated in the edges. So these are the weights. Okay, we have the 2, we have the 1, we have the 5, we have the 3. Okay. So these are the example of weighted graphs. So structures and structural metrics. Graph structures are used to isolate interesting or important sections of a graph. Structural metrics provide a measurement of a structural property of a graph. So global metrics refer to a whole graph, and then local metrics refer to a single node in a graph. So graph structures to identify the interesting sections of a graph. Interesting because they form a significant domain, specific structure, or because they significantly contribute to graph properties. So a subset of the nodes and edge in a graph that possess certain characteristics or relate to each other in particular ways. You will understand this more after we discuss some examples. Okay. So connectivity. A graph is connected if you can get from any node to any other by following a sequence of edge, or any two nodes are connected by a path. So a directed graph is strongly connected if there is a directed path from one node to any other node. So every disconnected graph can be split up into a number of connected components. So as shown on the screen, you have a disconnected graph here. Okay. Next is the degree. So number of edges incident on a node. So for example, the degree of 5 is 3. How come? So this is the 5. How did we arrive at 3? So number of edges incident on a node, we have what? Let me check my mouse. Okay, so I have here from 5, I have an edge 1 here, I have another edge here, so 2, and then I have another edge 3 here. Okay, so the degree of 5 is 3. So I have 3 incident edges. Okay, next. So degree, directed graphs. There are 2 categories of degree. Okay, we have the in degree and we have the out degree. So when you say in degree, it is entering or incoming. When you say out degree, it is leaving or outgoing. Okay, so last, for example, so let's check one by one. From the vertex 1, okay, from here, from the vertex 1, how many in-deg and how many out-degree do I have? So let's start with the out-degree. So out-degree, check the direction of the arc, okay, or of the edge. I have two outcoming, okay? I have two outgoing arcs. So that's why I have two here. What about incoming? Do I have any incoming arcs? No. So since I don't have any incoming arcs, I will put 0 for the vertex 1. Okay? Next, let's check the vertex 2. Okay? For the vertex 2, do I have any? Okay, do I have any incoming? Do I have any incoming for number 2? Yes. Why? From 1, I have 2 incoming. Next, do I have any out degree? This is 1, and this is the another 1. So, I will have 2. Let's try to check the vertex 3. Do I have any out degree? Do I have any out degree? Yes, I have 1. Okay. Next, do I have any incoming? I have 1, I have 2, I have 3, and this is a loop. So since this is a loop, I have 4. Okay? So that's the incoming, in degree and out degree. So simple facts about the degree. If G is a graph with M edges, so this is the formula. You can write it like this. Okay? So if G is a digraph, then you can write this the summation of indeg, okay, vertex is equals to the summation of out degree vertex is equals to E, okay, or edges. So number of odd degree nodes is even. Okay? So a walk of length k in a graph is a succession of k, okay, and then edges of the form. So this is just an example here. So this walk is denoted by wx and then xa, and is referred to as a walk between u and say. A walk is close is u is equals to say. So guys, this is just an example since the variables are given. So next is the path. A path is a walk in which all the edges and all the nodes are different. Okay? So this is the example. We have the graph here, which composes of the vertex 1, 2, 3, 4, 5, 6. Okay? Walk of length 5. So these are the example. Okay? We have the 1, 2, 5, 2, 3, 4 walk of length 5. We have the 1, 2, 5, 2, 3, 2, 1. So the CW length of 6. And we have the 1, 2, 3, 4, 6 for the path of length 4. Okay? So cycle. A cycle is a closed walk in which all the edges are different. Okay? So again, when you say a cycle, if you're going to create a cycle, make sure that you have different edges. Okay? So this is a cycle. So as you can see, the first vertex and the last vertex are the same because it is a cycle. And we have the 2, 3, 4, 5, 2 here for the 4 cycle. So we have a special type of graph. We have the empty graph or the edgeless graph. So no edge, as you can see here, we have the vertices, but there are no arcs or edges. So null graph, no nodes, obviously no edge. So these are the example of a special types of graph. So we have the empty graph or edgeless graph. We also have the null graph. So trees. So we have the connected acyclic graph. Two nodes have exactly one path between them. So meaning to say, there's no intersection. Okay. So we have the special trees. This is just an example. Next, here, regular. We have the connected graph. All nodes have the same degree. Okay. When you say same degree, for example, from vertex 1, I have 1, okay, 2, and 3 degree. Okay. So we have the degree of 3. Next, let's check 2. So 1, 2, and 3. Okay, same degree. Let's check 3. 1, 2, 3. Okay, so equal. Let's check 4. So 1, 2, and 3. So still, I have the same degree. Let's check 5. So 1, 2, 3. Okay, so I still have the same degree. Last one, let's check 6. From 6, I have 1, 2, 3. So as you can see, all the nodes have same degree of 3. Okay, let's move to the next slide. So we have a special regular graphs or cycles. Okay, this is an example of cycles. We have the C3, we have the C4, we have the C5. So next example of a type of graph is the bipartite graph. So B can be partitioned into two sets. Okay, we have the V1 and the V2 such that the UV is element of edges implies either U is an element of vertex 1 and V is an element of vertex 2. Or V is an element of B1 and U is an element of B2. Okay, so this is an example of bipartite graph. Next, we have the complete graph. So another type of the graph is the complete graph. So every pair of vertices are adjacent. Okay, these are the examples of complete graph. Next is an example of the complete bipartite graph. So bipartite variation of complete graph, every node of one set is connected to every other node on the other set. Okay, so as shown on the screen, we have three examples here of a complete bipartite graph. Next is we also have another type which is the planar graph. So can be drawn on a plane such that no two edges intersect. Okay, so again, no intersection for planar graph. So K4 is the largest complete graph that is planar. Subgraph. Vertex and edge sets are subsets of those G. A supergraph of a graph G is a graph that contains G as a subgraph. Okay, so as you can see here, on the right side, this is an example of a subgraph. Okay, so we have special subgraphs. We have the cliques. So a clique is a maximum complete connected subgraphs. Okay, so we also have the spanning subgraph. So subgraph H has the same vertex set as G, possibly not all the edges, so H spans G. So we also have the spanning tree. Let G be a connected graph, and a spanning tree in G is a subgraph of G that includes every node and is also a tree. So again, all the nodes are connected. Okay. So this is an example of spanning tree. So we also have the isomorphism. So we have the one-to-one mapping. U and V from the G are adjacent if and only if the function U and the function V are adjacent in H. So if an isomorphism can be constructed between two graphs, then we say those graphs are isomorphic. So this is an example of isomorphism problem. So we're going to determine whether two graphs are isomorphic. Okay? Next, we have the representation matrix. So incidence matrix, so vertex multiplied by edge. So it contains the edge data. So adjacency matrix, we have the V by V or vertex multiplied by vertex. Boolean values, adjacent or not, or edge weights. Okay? So for example, we have the graph here as shown on the left side of your screen. Okay? Let's try to answer this first. So we have here the 1, 2, 3, 4, 6, okay, for the vertices. So for example, do we have an edge 1 to 1? 1 on vertex 1, okay, none, okay, because we don't have a loop. Okay, next, do we have an edge from vertex 1 into 2 vertex? No. Yes, we have an edge here, okay, that's why we have 1 here. Next, from vertex 1, do we have an edge going to vertex 3? No. Okay? Because there's a middle vertex. That's why we will put 0. Okay? Next, from vertex 1, do we have a direct edge going to the vertex 4? No, there's no incident. So thus, we're going to put 0. Okay, next, from vertex 1, is there an incident or edge going to vertex 5? Yes. That's why we're going to put what? We're going to put 1. Next, from vertex 1, okay, is there an incident or an edge directly going to vertex 6? No. That's why we're going to put 0. Okay? Let's try vertex 2. From vertex 2, is there any edge going to vertex 1? Yes, we're going to put 1. What about 2? Going to vertex 2? We don't have a loop. That's why we're going to put 0. Next, vertex 2 going to vertex 3. Any incident or edge? Yes. That's why we're going to put what? We're going to put 1. Next, from vertex 2 going to vertex 4, any incident or edge? None. So that's why we're going to put 0. Next, vertex 2 going to vertex 5. Do we have an incident or an edge? Yes. So that's true. We're going to put what? We're going to put 1. From vertex 2 going to vertex 6, any incident or edge? None. We're going to put 0. Okay? Moving on to the next vertex, we have vertex 3. Okay? From vertex 3 going to vertex 1, any direct or any incident or edge going to vertex 1? None. We're going to put 0. Next, vertex 3 going to vertex 2? Yes. So I'm going to put 1. Vertex 3 going to vertex 3? Again, there is no loop. So false, we're going to put 0. Okay, next, vertex 3 going to vertex 4. Any incident? Yes. Okay, so we're going to put 1. Okay, next, vertex 3 going to vertex 5. Any incident? None. So we're going to put 0. Vertex 3 going to vertex 6 or any incident? None. So we're going to put 0. Next, let's check vertex 4. Vertex 4, do we have any incident or edge going to 1? None. We're going to put 0. Vertex 4 going to vertex 2, any direct link or edge or arc going to 2? None. So we're going to put again 0. So false. Next, vertex 4 going to vertex 3? Yes. So we're going to put 1 since it is true. Next, vertex 4 going to vertex 4. Any loop? None. So false, we're going to put 0. Next, vertex 4 going to vertex 5. Do we have a line or arc or any incident going to 5? Yes. So we're going to put 1. Next, vertex 4 going to vertex 6. Any incident or edge? Yes. So this is true. We're going to put what? We're going to put 1. Okay, next. We are on the vertex 5. Vertex 5 going to vertex 1. Yes, we have. So 1. Vertex 5 going to vertex 2. Yes, we have. So 1. Vertex 5 going to vertex 3. No direct link or edge. So meaning to say that is 0. Okay. Next, vertex 5 going to vertex 4. Yes, we have. And then vertex 5 going to vertex 5. No loop. So we're going to put 0 since it is false. Vertex 5 going to vertex 6. Any direct arc or edge? No. So 0. Next, vertex 6. Do we have an edge or arc going to vertex 1? None. 0. Okay, next. Vertex 6 going to vertex 2. Any edge or incident? None. So false. 0. Vertex 6 going to vertex 3. Any direct edge? None. 0. Okay, since it is false. Vertex 6 going to vertex 4? Yes. So we will have 1. Vertex 6 going to vertex 5. So no direct edge or incident. We're going to put 0. Next, vertex 6 going to vertex 6. So none, wala tayong loop. So it will be 0. Okay? So that's how you're going to do the matrix. Okay? It's almost the same with the upper part. Okay, it's just the vertices are already involved, and then you're just going to check if there is an incident or not. Okay? So next is representation list. We have the edge list and the adjacency list. For the edge list, pairs ordered if directed of vertices. So optionally, weight and other data. So adjacency list, node list. So implementation of a graph. So adjacency list representation, an array of V list, one for each vertex in V. So for each U element of vertex, so adjacency U points to all adjacent vertices. So here is an example of edge list for weighted graph. For example, okay, for example, from vertex 1, okay, I will go, the direction is what? Going to vertex, the arc is going to vertex 2, okay? So edge 1 to edge 2, I have a weight of 1.2, okay? Next, so since this is directed, I'm just going to follow the direction of the arcs. So next is vertex 2 going to vertex 4. I have a weight 0.2. So vertex 2 to 4, I have a weight 0.2. Next, vertex 4, just following the direction of the arcs. Vertex 4 going to vertex 5. Okay? I have a weight of 0.3. Okay? Next, that's the next one. I have the vertex 4, okay, going to vertex 1. I have the weight of 0.5. Okay, next, from vertex 5, following the direction of the arrow going to vertex 4, I have a weight of 0.5. Okay, next, from vertex 6 going to vertex 3, I have a weight of 1.5. Okay, so that's how you read the edge list for weighted graphs. Okay? So next is topological distance. So a shortest path is the minimum path connecting two nodes. The number of edges in the shortest path connecting P and Q is the topological distance between two nodes. Okay, so sometimes represented as D, so sub P and Q. So here is the distance matrix. So we have the example here. We have the graph here as shown in the screen. So for example, okay, we have the vertex 1 here. So we don't have a loop. That's why we have 0. Okay, from vertex 2. Okay, from vertex 2, we have 1. Okay, next, vertex 1 to 3. Okay, how many? We have what? We have 2 nodes. Okay, that's why we have 2. Okay, so that's the topological distance. So how many nodes is the distance between the vertices or the vertex? Okay, that's how you're going to read the distance matrix. Okay, just continue the reading for vertex 1. Okay, vertex 2, it's the same manner. Just check the vertices. Okay, next, to continue with our topic. So again, that's just a recap or a recall from the types of graph before we proceed with our actual topic. Okay. So class, if the meeting ends, kindly join again. Thank you. So again, this is just an example. So my everyday example for the greedy solution to optimization problem is we have the driving in Los Angeles, New York, or Boston. We have playing cards, invest on stocks, and then choose a university. So this is just an everyday example of greedy solution. Of course, when you say greedy solution, you're going to select the best, okay? What you know best. So a simple example, you're going to pick k numbers out of n numbers such that the sum of this k number is the largest. So for I is equals to 1, the initial value to k, pick out the largest number and delete this number from the input. So N4. So for this algorithm, you're just going to pick the highest or the maximum value. Okay, shortest path on a special graph. So problem, find the shortest path from B0 to B3. Okay, and then the greedy method can solve this problem. Now again, to find the shortest path, you're going to check the edges. Okay, so the answer here is 1 plus 2 plus 4 is equals to 7. Why? Let's check the actual graph. From vertex 0, I have a weight here of 1. We selected 1 because this is the lesser value compared to 5 and 3. Next, since we're looking for the shortest path, we're looking for the lowest value. From vertex 1, what is the lowest value? We have 10, 9, 2, and 6. So I will select the lowest value, which is 2. Okay? And then From vertex 2, I will select the edge that weights lesser, which is 4. So that is the shortest path from B0 to B3. I have what? I have 7. Because if I select, for example, I will select here number 1. Okay, from vertex 0 to vertex 1, I will have 1. Okay, next. From vertex 1, I will select 6 to vertex 2. So I have 6 here. And then next, I will, from vertex 2 to 3, I will select 4. So if you're going to sum it up, I will have what? I will have 11. So again, look for the shortest path for this graph, and the answer, and that will be the answer. So the answer is from B0 to B1, I have 1. From B1 to B2, I have 2 weight. And then from B2 to B3, I have the weight of 4. So this is again the shortest path. So the lowest value. Okay? So this is an example of another example for the shortest path from B0 to B3 in the multi-stage graph. Okay? So if you can see, we have a lot of values here. We have the vertices, we have the V0, we have the V11, we have the V12, we have the V13, we have the V14. We also have the vertex 2, 1, we have the vertex 2, 2, we have the vertex 2, 3, and we have the vertex 3. Now let's try to check this one. How did they arrive with 23? Okay. From B0, okay, let's try to select 1 since this is the lowest value. And then let's try to select this one. Okay, we have the V12. We're just going to compute for this one. We have the 9. Okay. And then we have the B21, which is 13. Okay. To sum it up, 13 plus 9, we have 21, and then we have 22. Okay. You can either select another path. You can select again 1. Okay. And then next is what? You can select again, let's say here. So from here, V12 to V22. So we need to have the edge. We have the 16. And then we can have V22 to V3. We have 1. Okay. So from here, if you are going to apply the greedy method, of course, you're going to look for the best. You're going to look for the highest value, which will not work for looking at the shortest path, because the shortest path is the what? The lowest value. Okay? So meaning to say, greedy method is not applicable here for looking at the shortest path. So you can apply the optimal. Since the optimal value will produce you what? You can look for the lowest value, which is 7. Okay? Okay. So shortest path problems, we have the directed weighted graph. Path length is sum of weights of edges on a path. And then the vertex at which the path begins at is the source vertex. The vertex at which the path ends is the destination vertex. So let's try the example here. So apart from 1 to 7, so we have vertex 1, vertex 2, 3, 4, 5, 6, 7. So if you're going to check the path from vertex 1 to vertex 7, we have the path length is equals to 14, or the weight is 14. Okay? Next, let's look for a different path from 1 to 7. So we have, okay. So the first example is from 1 to 7, we have the 14. Now, looking for another direction. So from vertex 1 to vertex 3, we have 2. Okay? Next, from vertex 3 to vertex following the direction of the arrow, vertex 3 to vertex 6, we have 8. Okay? And then from vertex 6 into vertex 7, we have 1. So that's why we will arrive at 11. Okay? So that's the another direction. Okay, next, shortest path problems. So the single source, single destination, single source, all destinations, and then all pairs. Every vertex is a source and destination. So single source, single destination. So possible greedy algorithm. Leave source vertex using cheapest or shortest edge. Leave new vertex using cheapest edge subject to the constraint that a new vertex is reached. Continue until decision is reached. So now let's try to apply the greedy shortest 1 to 7 path or direction. So the path length here is 12. Okay, as you can see here. Okay, just following the arrow. So we have here 2. We have here following the direction of the arrow from vertex 1 to vertex 3, we have 2. From vertex 3 to 5, we have 3. Okay. Next, from vertex 5 to vertex 4, we have 4. And then from vertex 4 to vertex 7, we have 3. Okay. So that is 2 plus 3 plus 4 and then plus 3. Okay, that's how we arrive at 12. So again, now for the greedy shortest 1 to 7, so path length is 12, so not shortest path algorithm doesn't work. Okay, so we have single source all destination, so need to generate up to n is number of vertices. So paths including path from source to itself, so greedy method, construct this up to n paths and then in order of increasing length. Assume edge cost lengths are greater than or equal to 0. So no path has length less than 0. First shortest path is from the source vertex to itself. The length of this path is 0. Okay, let's try this one. So we have the same graph. Okay, so now, so from vertex 1, do we have any length? So 0. Next, from vertex 1 into 3, going to vertex 3, we have length 2. Okay? So now, let's check the next path or next direction. So we have from vertex 1, okay, to vertex 3 and to vertex 5. So 2 plus 3, we have the length of 5. Okay? Next, what about vertex 1 going to vertex 2? Is there any edge? Yes, we have. The weight is 6. Okay? That's how we arrive at 6. Next, the next path or destination from 1 to 1, 3, 5, and then 4. Okay? So from 1 to 3, we have 2. And then from 3 to 5, we have 3. And then 5 to 4, we have, okay, 4. So 2 plus 3, 5 plus 4, we have 9. Okay? So next direction is the 1, 3, and 6. Okay? From here, 1 to 3, we have 2. And then 3 to 6, we have 8. So that's why we have 8 length here. So next direction, so 1 to 3, okay, we have 2. Okay, sorry. We have 2. And then 3 to 6, we have 8. And then 6 to 7, we have 1. Okay, that's why we have 11. Okay, so checking all destinations. Next, so greedy single source, all these destinations. So again, so just to enumerate, from path 1, we have 0. From vertex 1 going to vertex 3, we have length 2. And then vertex 1, 3, and 5. So vertices 1, 3, 5, we have length 5. And then vertices 1, 2, we have 6. Vertices 1, 3, 5, 4, we have 9. And then vertices 1, 3, 6, we have 10. And then vertices 1, 3, 6, 7, we have 11. So each path is a one edge extension of a previous path. So next shortest path is the shortest one edge extension of an already generated shortest path. Okay?